Hey everyone, how are we doing? It is time for office hours. If you're in the chat, feel free to ask what you want. My hair is all crazy today. Hey Jesse, good to see you here. Let me make sure Mewbot's awake. Waking up Mewbot right there. Mewbot is waking up. And we could start out. I was thinking about doing the formula sheet and putting that in the video, like everyone could see like what's on the formula sheet, what we have to do. We were to stat to on it. Whatever you'd like though. Pulling up the review material. Because the exam is coming up. Mewbot is waking up. Let's see. Could we do more of Canvas content yet? 10? Let's do it. Let's start with some Canvas content 10 and review how to do it. Canvas content 10 is where we will start out. And remember how to solve the questions. That's always going to be the key, is like, how do we solve this question? So here we go. Canvas content number 10 right here coming up. Got everything open, ready to go. Looking good. And so here we go. Stat tool 1, Canvas content 10. Let's do it. Here we get everything open. What's up, Philip? Good to see you. 100 points, Philip, in the chat. Let's get going and do it. Okay. Canvas content number 10. Here it is right here. Good to see you, Matthew. I told them they have a week, so they're supposed to abide by the week. Some people already have some grades. I think I've published them all, but they have 1 week to grade them. And I'm going to make sure I'm going to be emailing them. One of my graders is already done. Thank you so much. But yeah, please let me know if there's an issue. SAR grading sometimes has been a little bit slow. I do. And once again, huge thank you to the graders. Yeah, so let's see. They should be graded in 1 week max. But they do have finals too. But they do grading. The results of a chi-square test for independence concludes color choice is dependent on the kindergartner. What percent submitted early? It was like 60-70%. Thank you to all the students who submitted early. We had a very, 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 very high percent submitting early. And here, let's take a look at this. Says it concludes dependent. Well, whenever you do the chi-square test of independence, yeah, I was very pleased with the percent that turned in early. Very, very pleased. Whenever you do the chi-square test of independence, what is the null hypothesis? Like, this is something we should know like that. For the chi-square test of independence, the null hypothesis is what? So you do the chi-square test of independence. How would you best summarize the null hypothesis? And let's look over here at somebody's, let's say, Greek life explains your distance to campus. Now, this is the chi-square test of independence. Why? Why am I going to be doing the chi-squared test of independence for the distance, like if someone lives in the fort or on campus or 30 minutes away in their Greek life? So why would I be doing the chi-squared test of independence here? These are big things to know about the chi-squared test of independence. One of the conditions, condition number 4, I like to call it the 4th, is that you have 2 categorical variables. So since we have Greek life and distance from campus as a categorical variable, we'll be doing the chi-squared test of independence. Now, the null hypothesis would be that somebody's Greek life affiliation, good to see you here, Nicole, 2 categorical variables, count, data, condition. The null hypothesis would be that somebody's distance from campus is independent of whether or not they're in Greek life. And what do we do right here? What do we very clearly do? We very clearly what here because of that. So remember, the Pearson has your p-value. So very clearly, we are going to what here. Very clearly, because the p-value is low, we are going to what. And we need to know, so I'll people think about that, what we're talking about. Whenever you do the null hypothesis, and we just said it a second ago, make sure to go in here, look at your variables, reject the null exactly. So the null hypothesis simply is adding the word independent between these. We don't use notation for it. We just say that someone's distance from campus is independent of them being in Greek life. We reject that. So we would have what here? So with the p-value of 0.0001 or less than that, less than 0.0001, I think there's another 0, which is less than my alpha level of 0.05, I reject the null that these 2 variables are independent of each other, that distance is independent of someone being in Greek life. I have what? So we've kind of done the full chi-square test of independence on this. Because my p-value of 0.00001, got a lot of zeros, is less than the alpha of 0.05, I reject the null hypothesis that someone's distance from campus is independent of them being in Greek life. I have evidence for somebody's what? I have evidence that they are dependent. Great job, Jesse, right there. Keep it up. We'll throw some bigger points here in a moment. And so when you look at this right here, it says they found evidence of dependency. So what must they have done if they found evidence of dependency? Well, then the p-value was lower than alpha, which is exactly what we just did on ours, where we said our p-value was less than alpha. We have evidence of a dependency because we reject the null. So basically, I tried to work an example where we came to the same conclusion, where we concluded evidence of a dependency, and it was because the p-value was less than alpha, and that's kind of the full example. The chi-square test of independence, larger values of chi-square test statistics indicate a cause and effect relationship. Hey, Caroline, good to see you. Feel free to ask any questions. So be very careful on this one. Now, there's words we don't say in this class. Yeah, we'll be doing that here soon, Claire. Might pop up on this one. What are words we don't say in this class? We don't say a certain C word over there. We don't say a certain P word. You can say them now. The words we don't say in statistics. What words do we not say? One of them is in this sentence. We don't talk about things being a cause and effect relationship. We don't say prove. We don't like to say no. We would never say, I know this. I can prove this. We say we have evidence. We have good reason to believe. That's how statisticians talk. Like, here's what the evidence shows. Here's my current belief. We don't say we cause or prove things. Now, what is true, and MuBots just put the chi-square test or the chi-square distribution, make sure to know when it comes to the chi-squared, I'm just going to enter in a good bit, that if the chi-squared value is larger, the p-value will be water. If the chi-squared value, which I'm changing up here, is larger, then the p-value will be water. I'm increasing the chi-squared right now. Great job right there, Nicole. So if the chi-squared is larger, the p-value gets water. As the chi-squared gets larger, or for larger values of chi-squared, p-values are water. So you see right here, we start with a chi-squared of 0, and then we start making the chi-squared larger, and you can see what's happening to the p-value, which is the area to the right of our result, showing a result more extreme, and the probability of it. P-values get smaller. That's because this is the standardized discrepancy, and bigger discrepancies are less likely to happen by random chance, so kind of good to know that right there, but they don't prove that there's a relationship. So that's false. They don't prove it. The degrees of freedom. Okay, so what's our trick? We say, Brian, this is a what by what. So don't even read their answer yet. Let's find the degrees of freedom. Brian, now be careful. A lot of people get this wrong every once in a while. I feel say in class like, Brian, that's a blank by blank. So I'll let you tell me what that is a blank by blank by. Brian, that's a blank by blank. How many rows, how many columns? Be careful. There's a mistake that commonly happens right here. It's a 5 by 2. I think it is. Great job, Jesse, right there. So we got 1, 2, so 2 by something. You can 5 by 2 or 2 by 5. And then 3, 4, 5. Do not count the totals. Do not count the totals. Those are not groups. So if it's a 2 by 5 or 5 by 2, what's the formula? First, tell me the formula for the degrees of freedom, which will be easy to solve. What is the formula? Don't count the totals right there. A lot of people do that by accident. What is the formula for the degrees of freedom? Like, what numbers are you going to multiply? So once you know it's a 5 by 2, you simply take the numbers. Usually it's small enough you can just do it on your hands right here. And then you do what? So there's the formula right there. And you do rows minus 1 times columns minus 1. So you just drop one finger, right? So if it's a 5 by 2, I got to make sure my thumb's down. You just have 4 times 1, and the answer is 4 degrees of freedom. Now, it asked us, it said the degrees of freedom are 5, so that is false. The degrees of freedom are 4. We probably should have put in, like, the degrees of freedom are 4. I don't know. Or put in something you could get that's wrong right here. That's a false statement. Right here, it wants based on the jump output, what is the corresponding level of significance to the confidence interval? So whenever you do a confidence interval, the confidence interval is the area where on the curve. Whenever we are doing confidence intervals are the area where on the curve. So think about how confidence intervals are made. So if we have the t distribution right here, let's give it like 50 degrees of freedom. Confidence intervals are the area where on the curve. So if we have a t interval, a confidence interval is going to be the area where. There are other ways to make confidence intervals, but we usually make a general confidence interval that has area where? Above, below, between, outside. Between, great job, Sheena, right there. So between, right? That's the area. 95% of the area is contained between this. So with the between, a 95% confidence interval would work the same as a test done with what alpha level for the two-tailed test. So a 95% confidence interval would work the same as a two-tailed test with what alpha level? Remember the two-tailed here. What would be the alpha level of the two-tailed test? And you see the t statistic right there. We can confirm the answer. So what would be the answer for this? 95% confidence interval would have the same conclusion as a t-test done with this alpha level on the two-tailed test. So 95% confidence. Think about the way the two-tailed test is run, and what would be the alpha level corresponding to the same conclusion of a 95% confidence interval. So if 95% is inside, then how can we figure out what the two-tailed test would do or correspond to and come to the same result? So 95 is the big hint, and then think about the tails over here. Because I'm going to go to between and make it look the same and get the same value. So would it be like, or it's 95, would it be like that? Would it be like this? What would it be for the outside, which is the two-tailed test? What would it be if it's 95% inside? If it's 95% inside, then it'd be what outside for the two-tailed test? And remember, we have a value over here. Yeah, exactly, Jesse. So it's 95% inside. Do you see this value right here? And what we can do is we can confirm it by taking a quick screenshot and then going over here, go to outside. And do you see how it's the same value? So right there, that concludes we're doing the same sort of mechanical test. So what's a quick formula? If 95% is inside, the two-tailed test would just be what? And here's the confidence right here. So what would be the corresponding right there? How could we then figure out the answer to this to figure out the outside? Because we're just doing the same trick. We're going to just take the outside of it. If this percent is inside, let's just get the outside. How would we then figure out the corresponding two-tailed test and the alpha level used for it? The corresponding alpha level would be what? How would we figure that out? The key is to know how to solve these, which we're doing right here. So remember, the other one was not. That's just it. Great job right there, Caroline. Yep. 1 minus. Here, let's do it. 1 minus, and there it is right there. There's the answer. Which is not a way to check the nearly normal condition. So the nearly normal condition is when we have quantitative data. So let's go ahead and take somebody's age right here. And let's go ahead and stack it. And that's kind of only a little bit skewed. So this is the checking of the nearly normal condition. Let's see which answers it gives. Might be able to get it on the screen at one time. Or maybe not. The central limit theorem. The central limit theorem is the large enough n condition. I could bring up the applet again. We're going to do some more here, so I might not. The central limit theorem is the large enough n. That is, n gets larger, the distribution of the mean will become more normal. A goodness of fit test is where you fit a normal curve onto your data, and then you see if it is a good fit. And the answer is, there it is right there. We see that this is not a good fit because the null hypothesis is that it is a good fit, and there's evidence that the normal curve is not a good fit, especially over there. The histogram is what we're literally seeing right here. Degrees of freedom greater than 10? I don't recall a way of doing that. More degrees of freedom is better, which kind of relates to the central limit theorem. But the last way up here is the normal quantile plot, also known as a normal probability plot, which shows you the probability your distribution is normal. So you can see all these methods here, except for degrees of freedom greater than 10. That's not a way we determine if things are nearly normal. Of course, if there are enough degrees of freedom, you could use the central limit theorem, but you can't just say degrees of freedom are at least 10 and it's good. Now, calculating the t, I guess we could talk over that one because we didn't get it, and I'll see if it appears here. It's a lot of good output. This one's good too. We'll do calculating the t next. Okay. So what do you know about p-values? Well, first off, let's look at this output, and then I'll basically give the answer for calculating the t. So let's grab this output right here. And this is the, I think it's like the speeds of USA runners and Australian runners, like how fast they are. So this is super important, knowing all of this output. Since the difference was positive, which mean was higher? So what we did is we took, if this is speed, then the men certain numbers lower. USA, mean for USA minus mean for Australia. Oh, a little off the screen right there. There we go. And so since the difference here is positive, which mean was bigger? And I know it's set up this way because of that right there. So since the difference is positive, which of the means was higher when we took a sample of USA and took a sample of Australia? Which mean was higher? So just plug in some fake numbers right here. Plug in like 8 minus 2 and see how the difference comes out. Now notice that the difference right here, you can look for the sign, or if there is one in front of it, USA was higher, exactly. So the mean for USA was higher by 0.043. The standard error, we're going to zoom out just a little bit here. This is y bar 1 minus y bar 2. The standard error is square root s sub 1, which we don't have, n sub 1, which we don't have, plus s sub 2 squared over n sub 2. That's the standard error. Yeah, And so thank you, Aileen, right there. We'll do those here soon. With this, we have the standard error and we have the difference. How is this number right here calculated? Like, show me the math for that. So the formula for the t statistic is that the t statistic, which this is right here, is equal to y bar 1 minus y bar 2 over s sub 1 squared over n sub 1 square root plus s sub 2 squared over n sub 2. So what is the math you could do to find the t? How could you find the t? So there's the formula you'd need to solve. To find the t, you'd have to take the difference, which that's that right there, and divide it by the standard error. So how could you find that 2.5 right there? Like mathematically. How could you find that? What numbers would you divide? This goes to another person's question about how to get the t ratio right there, which is the t statistic for the two sample t. Yep, that's it, Jesse. Great job, Jesse, right there. That's all you got to do is just divide those numbers. If you divide the difference, which is 0.04 divided by 0.017, you get the t statistic. So this number right here, this thing right here, is just these two numbers divided, which I'm trying to show it there. The degrees of freedom, basically this means we're very close to a normal curve because the degrees of freedom are very high. The confidence interval is I am 95% confident the true difference between USA men or US, I think we've done like men sports or something. I am 95% confident the true difference between USA and Australia is contained in the interval between 0.009 and 0.077, whatever we're measuring right here, if it's like speed or seconds in time, where USA men had a higher mean. So this is the true difference between their means, and since the difference is positive, it's evidence the first mean is higher. So make sure you know how to interpret that. I am 95% confident the true difference in means between USA and Australia is contained in the interval 0.009 to 0.077 when there is evidence that the mean for USA men is higher. So now we get to the p-values. The p-values, there's 3 of them because there's 3 what's to the what. There's 3 p-values because there's 3 what's to the what. There's 3 p-values because there's 3, and it kind of goes to this right here. There we go. There's 3 what's to the what. There are 3 signs to the alternative: greater than, not equal to, and less than. So now we go right here and we draw a normal curve, or basically, because it's a normal that's looking like a normal now, because it's a t that looks like a normal. Signs the alternative. Great job, Jesse. And so we landed at a t of 2.5, which is going to be over here somewhere. So we're going to mark that on each of the curves. I wish my curves looked perfectly identical. There we go. So that's meant to be the same spot on each of the curves. My drawings vary a little bit because, oh, let's do it the easy way to make the drawings perfect. Okay, we're going to go here, copy, and move these down. And now the curves are the same, and I've got them pretty well lined up. And now with the curves pretty much this, or exactly the same, we're going to do a line. Get straight. There we go. And now the less than graphs to the left. The greater than graphs to the right. And that should give us a hint. We know that the less than is 0.9934. So what does... Hey, Sloan, good to see you here. Yeah, Elijah, good work. And so then how... oh my gosh, I'm so zoomed in you can't see it. How are we then going to find the greater than? How do we find the greater than probability right here? How do we find the greater than probability? So think about, we're looking for the area here. So how would we figure out the greater than probability? So think, if this is the area over here, that's 99.34% of the area, then how would we find this? So we're just thinking about the area to the right of the line. If the area to the left is 99.34, what's the area to the right? Exactly. So we just do the complement right here. Now we get to the harder one, but it's not that bad. I've done it right. So now if you look at this visually, how do we find the does not equals? Hey, Patrick, good to see you here. So the does not equals, think about what it's doing right here, because we're going to negative 2.5. Exactly. Great job, Jesse. So the reason is the does not equals is on the other side of the curve, or we reflect the area, and we're just going to multiply that by 2. So all you're doing is just taking this area over here and reflecting it over to the other side, doing a 2 times. And so understanding this output right here, what it's showing you is the key to, doing well on the test. So make sure you know your output. I think that mostly does it. We've done all the questions right here. It wants the does not equals test. Notice here the does not equal sign, which is this test right here. There's the p-value. What is the corresponding alpha level? Same thing we had earlier. So 0.077. I think that's right. Yep. Check out earlier. A contingency table is a key component in the chi-square test of independence. True or false? A contingency table is a key component of the chi-square test of independence. True or false? Here's a mosaic plot. Here's a contingency table. Someone got it right there. True. And there's the chi-square test of independence. So the contingency table shows you the numbers. That is very true. In the chi-square test of independence, large values show a cause and effect. False. Include the p-value is lower than alpha because we rejected the null. Yep. And yeah. Does that make sense, Jesse? I know attendance is in the day one bonus for points count on Canvas. Also, they point added. Yep. I'll be adding up. Good questions there, Brett. I'll be adding up all the bonuses here at the end of the semester. Lots of bonuses. And how are we doing at that? Hey, let's go check us out. How do people think we're doing at TN Voice? We got to do some big announcements today. Let me go look at TN Voice right now. I'm like, oh my gosh. So no, I bet we're at 55%. Probably have like a day or two left. I say we're at 55%. What percent do you say we're at? I say 55. Do that TN Voice. Do it for all your teachers, even the ones that don't give you extra credit. They are counting. I haven't added them yet. Yeah, that's the problem with online classes. Morning class is at 64%. Afternoon class is at 52%. I'm shocked it's at 64%. I'm very happy about that. 80% is very good. I think that's where we get our second bonus. But here, I'll send out a reminder and be like, quick reminder, TN Voice, there is bonus on the final. Just takes a moment. So do it, please. Very important. I'll go send out an announcement here while we talk about this and say TN Voice. TN Voice bonus still available. TN bonus for doing TN Voice. Time running out. I say time running out, but tomorrow will be the last day, so I'll send an announcement tomorrow about it being the last day. Okay, got it. Good. It always goes like this links to an external site. TN Voice is still open, but not for long. TN Voice is still open. Okay. Send. Get a few more with that right there. More people have done the TM voice than show up to class. Well, that's good right there, right? I think we need, like, what did Terry say? Let me look at what Terry said. Play one more time here. Oh, here we go. 60, 80, 90. So we already have 1 point in one class. I think we can get to 80 in both classes, I think. 90% completion. It's really rare. No, the 90 is the +3 right there, Sloan. So it's 60, 80, 90, 1, 2, 3. But 90 is really hard. Like, I'll just flat out tell you that it's very hard to get over that 90%. My best online classes have gotten like mid 80s. And this is gonna be some of our best. We're doing pretty well, I think, actually. Like, there's a lot of people who do it at the very end. We can't tell who did TN voice. Like, I have no idea who did it or didn't, because they wouldn't want us to know that. Imagine if you had like 3 people in there, like you could see who did the TN voice, then it wouldn't be that anonymous. Like, totally anonymous. And I totally understand, like, but yeah, I like to be the team effort. Yeah. So we could review the formula sheet. Thoughts on that? I think you're doing great. We're 52%. That's why I said we're out, right? Already closed out, I think. Nope, so we're here. 64 and 52%. Yeah. Let's get more people to do it. Woohoo! I think it's super helpful for us. Oh, thank you. Well, I appreciate that, Sloan. You're welcome to do that. I can't wait. I love reading them. I feel like we're having a great semester. Sometimes I'm a little bit afraid. It's like my grades. You ever get afraid to look at your grades? You're like, oh, grades are in. I'm afraid to look at it. So sometimes I'm a little bit afraid. Like, I'm like wondering, are people going to be angry with me? Or are they going to be like, this class is horrible? I don't know. It's my grades. So yeah. Let's go to the main screen. Oh, thank you. Here we go. Let's talk about the formula review sheet. So this section right here is going to be, says Stat 201, the formula sheet, and one sample proportion. Okay, so with this right here, we're going over the formula sheet, each step right here and what it means. Let's start with the one sample proportion right here and talk about what each of these means and explain every single bit of notation on the screen. So you need to know all the notation right here, every bit of it. First off, what is p hat, and can you write a sentence where you give someone the information for p hat? So that's your goal right here. If you're watching this video in the future, try writing a sentence right now for any of these, especially p hat to start, where you would say something like, we went out and talked to 100 students and 40 of them own dogs. So p hat would be 0.4. The information you just heard in that question was x equal to 40, or that statement, and n equals to 100. So that was the information you got right there, the sample size and the amount of successes, which is x. You could also have changed the numbers to be a little bit harder, where we say something like this, and now we have x over n equals p hat, and thus 40 over 200 is equal to 0.20, which is the proportion. Basically a percent, and that is the sample proportion. So first thing we know right there, p hat is the sample proportion. It comes from a sample size. It's found by how many people conform to whatever we asked the question of, do you own a dog? Has to be categorical. Very important. Proportions are for categorical data. So we need to know that right there too. A confidence interval is going to have you pick the z. So that's different than this z down here, which is a standardized difference. So when you give the z, it's relative to a level of confidence. So there's going to be a confidence level right here relative to that z. So you might say, I am 95% confident, and that would be a z of 1.96, technically. Or you might say something like, I am 98% confident, and it would be 2.3263. Now, you're not meant to remember those. 95 is basically 2, but here's the thing. As we get more confident, the z-square gets bigger because you're going to be shading more of the curve. When you go from something like 95% confident to 98, you have to shade more of the inner portion of the curve, so you're expanding the z-square. Good to see you, Sheena. We have to find the two. Which one is that, Sheena? Which problem is that? And I think we have everything. I think we did all the problems during class last time. So I think we did all chapter 19, right? We did all the homework and all the quizzes, right? Maybe. Tell me if we didn't. But which one specifically we have to find the chi-squared. Awesome. Awesome. We can check that out here soon. You got it. Ooh, so much going on. Wee. So the Z right there is relative to the percent confident we are. Next, we see the standard error of P hat. And I don't like to write it out as the standard error of P hat. This is your classic P times Q over N square root. But it's P hat Q hat. Oh, yeah, let's do it here. And then we'll do it here next. So this is P hat Q hat. And Q hat is 1 minus P hat right there. So Q hat is the complement of P hat. So if you know that P hat is 0.8, Q hat is 0.2. So that is how we get P hat and Q hat. They're complements of each other. That is how we make a confidence interval, is we have our estimate of the truth. Then we have a margin of error created by the plus or minus right here. There's the confidence interval. We'll do your question next. Thank you, Sheena, right there. And then the test down below, we always say a test is a difference standardized. So let's look at what this difference is. So there's the difference standardized. The difference up top is going to be what you saw in your sample, the sample proportion, minus a hypothesized proportion. Now, the hypothesized proportion is just going to be some number you come up with. It might be something you want to test. Like, do you think 70% of people own a dog? Well, that's your hypothesized amount. P naught does not come from data. It comes from your question. So when you say P naught is 70%, you're saying I hypothesize that the true proportion is 70%. So what we do is we write it in the null hypothesis where the true proportion is equal to what we hypothesize. Now this value just gets input right there. So whatever we put for P naught gets put over here, and then we switch the signs of the alternative. So the alternative just has a sign change, like if we're going to test if it's not equal to. And there we go right there. So that's how we run the test right there. Lots of steps running the test. Last but not least, this is called a standard error. It's a little bit confusing why it's called a standard error, but let me explain it this way, even though it's a little confusing, is it's based on the truth. If you notice right here, we're using P naught and Q naught, and P naught is assumed to be equal to P. So we basically believe right now we're doing P times Q over N square root, which is the standard deviation. So because we're assuming we're using the truth, then we call this the standard deviation rather than the standard error, which is calculated using sample statistics. So very small differences right there, but understanding the notation, and Q naught would be just found by doing 1 minus P naught. So Q naught is equal to 0.30. So really good stuff to understand right here. Sheena, let's go ahead and do your question. You got it. Okay. We have to find the... Which question is it, Sheena? Can you tell me which one it is? Which homework or quiz problem? We're going to log into my Pearson right here. And which one is it? Yeah. Knowing all the notations is the key to solving problems. Like, that is a major, major help. If you know the notation, it's way easier to walk through the problem. If you don't know the notation, it gets a little bit scary as you work through the problem. It can get a little bit difficult quickly. Pregnancies. Here we'll do the pregnancy one on the homework. Let's take a look. Pregnancy one. Thank you, Sheena, so much. Let me throw 8,000 points. I appreciate it. Please, if anything's ever confusing, let me know. A lot of times, and I try to explain it in a different way, because it's these things. I think once you grasp it, it's like, oh, but it can seem like magic at times. We don't want it to seem that way. We want it to be like, okay, I get it. I see how to do it. Let's see right here. I think it's the very last one. Most pregnancies. Okay, here we go. Well, let's go check it out. So the first thing we always do when we write the null hypothesis for the chi-square test of independence, what is the key word we need to know every time we do the null hypothesis? For the chi-square test of independence, and don't look at their answers, always try to think of your own answers first. The chi-square test of independence, null is the independent. Let me go mark the video right here real quick. Thank you so much. We always say that they are independent of each other. 36, 33, stat tool 1. Chapter 19 quiz. Greatest. Most greatest. Okay. So we'd say here, great job, Emma, right there. We'll throw some points out. We would say that somebody's age group is independent of the length of their pregnancy. The alternative would be that they are not independent. So pretty easy right there. The age group and outcome are independent. The age group and outcome are not independent. Now, when you do this question right here, it immediately jumps to the end of it. There's a lot of steps you'd have to do to solve this on your own, but I highly suggest using jump. I'm going to show you right here how to solve it not using jump, and it's not fun. So this is how you have to solve it if you don't use jump. So let's do some practice right here, and I'm actually going to use, well, it's not fun. I'm going to watch this. I'm going to get something I need right here. Copy to clipboard, and I'll show you the steps. I'm just doing this quicker. We'll come back and use jump here in a second. Tables. I'm doing analyze. Okay, we're almost there to where I can show you again. Okay. So we were missing one very important thing in the table. What is the difference? Sloane's already on track with it. What is the difference between my table here and their table? What is a key difference that I really wanted that my table has now? In solving this, my table has, and it doesn't matter if the X and the Y are reversed, my table now has what? The totals. So that's what I wanted right there. I wanted the totals to help me solve this. So you could find the totals yourself, but now we've got the totals to work with, and here we go. So the first thing is first. The counts, how would you explain what counts are to people? How would you explain what counts are to people? Counts are what you what? How would you explain what counts are? There's another word I like to say for them. The counts are what you what? What does a count mean? Or frequency? What are the counts? Does our final contain more or less? It's everything test 3. It's everything, and I can show the syllabus. Good question, Nicole, right there. And check out review 3. There are the tools and techniques questions. Review 3 does a great job covering them. Good questions, Nicole. So what are the counts like? What does 129 mean? So like, what does the value of 129 mean if you had to tell somebody? These right here. So these are the counts. These values highlighted in pink are the counts. So what are the counts? Like, what is 129? So 129 is a count. But what is a count? What does that mean? What does count mean? Like, how would you explain what the value of 129 means to somebody? Great job, Sheena, right there. There are 129 women under 20 who had an early preterm. It's how many individuals you count in that group. It's the frequency of the observations. It's the observed amount. It's how many you observed. Does that make sense? The count is the observed amount of people in that group. So now, what we need to do is we need to calculate how many we expect via random chance if the null is true. To do that, we need to do the following formula: row total times column total over grand total. So how many women under 20 would you expect to be early term? So remember, it's row total times column total over grand total equals to expected. So how many would you expect? So solve the formula right here, and this will get you the expected amount. There we go. Sloane's got it right there. And we're just doing this formula that is right here. The formula that I'm showing you right here is the formula to get the expected. Great job right there, Sheena and Sloane. So here's the thing, though. If you are doing this, how many times total will you have to do this? So you just found the expected amount of 120.55. How many times will you have to find an expected cell? How many expected cells are there? just like the counts, how many expected cells will you get? If you're doing this by hand, you'll have to do it. Three more times on that row, correct? So you have to do it. You just did here. 1, 2, 3. Well, not 4 total. So there'll be 3 more times on that row. And then how many more times will you do it? Like, or how many times in total will you find expecteds? Because every observed has an expected. Not 12. Not 12. Good guess right there. Not 12. Close. So remember, don't do the totals. Oh, wait. Yep. I have it right. I thought I made a mistake. So not a total of 12 times. 8. Great job, Nicole, right there. I'll show you some points. Because this is a what by what table. You will do it 8 times total because this is a what by what table. So just think like, oh, it's a blank by blank table. Remember, don't use the totals. Be like, yeah, I'll have to do it 8 times. 2 by 4. Yep, great job right there, Sloan. We got this. So now we're going to go over here and use the data here and watch this. We're going to only look at the expecteds. So this is theoretically if you went and found all the expecteds on your own. Does that make sense? Could you do this right now? Could you go and find every single expected on your own? We just found this one up here, and here it is down here. You could go, yeah, the totals, yeah, it can get confusing. And so now you could have gone and done this formula for each one of these. So that's the cumbersome part of it where I'm just like, I don't want to do that. But now what do you do next? Now that you have your observed, which is the count, and you have your expected, which literally says expected, what formula do you do next in the process of finding the chi-squared test statistic? So go ahead and try to solve it for this cell right here. So what I'm asking you for is the chi-squared test statistic, and I'm writing out the formula down below for the cell chi-squared. We take the difference between the two, we square it to make it positive, we divide by the expected to standardize it, and that gives us a cell chi-squared. So that's a cell chi-squared. So what would be the cell chi-squared for this cell? What is the cell chi-squared? Who knows the cell chi-squared? It's going to be 9 squared over 81 about. It's going to be about about 0.6 or something. It sounds to be. So we just plug in the numbers. That was a little smaller than that, but 120.547. Oh, because that's not quite 9. So we go right here, we take the top and subtract 120.547, square that, divide by 120.547, and the cell chi-squared. Perfect job right there. So the cell chi-squared for this cell is equal to 0.0592. Now, how many times do we have to get cell chi-squareds? How many cell chi-squareds will there be? I'll give you a hint. There will be how many cell chi-squareds? How many cell chi-squareds will there be? How many cell chi-squareds will there be? There'll be a total of 8, each one for each cell. So if you notice, we can do this process for everything right here. We can find all the expecteds. We have to have the observed to start. We can find all the expecteds, just doing the same process here. We can do all so the numbers you're taking, I'll circle them in green right here. These are the numbers you're using where it's the observed minus expected. Make sure this is the observed, this is the expected, and this is the observed, expected right there. So there's the formula kind of annotated a little bit with color notation to help out, and that's going to lead to this one right there, specifically right there. And so with this, we now have all the cell chi-squareds, and the last process right here to get the chi-squared test statistic is going to be to what? The last part of this process to get the chi-squared test statistic is going to be what? All the cell chi-squareds. So what are we going to do to all the cell chi-squareds to get the chi-squared test statistic? I'm going to add them up. So the sum of the cell chi-squareds is the chi-squared test statistic. And so you could literally go over here and add them. 0.269 plus 0.112. And it's not bad to solve a few of these by hand just to practice, because then you'll really understand like how to do this. You'll be like, okay, I solved one of these by hand, and it took a while, and just you start to remember the process a little bit better of finding these standardized differences, and you can get to the point where you're like, I know what I'm looking for, and I know the steps and what I need. So 2.986, and we would have to do that right there. Go back over here. 2.986. Did I make an error when I was adding them? I did not. But here's the problem, or here's the thing. That takes way too much time. So this is how to solve it. Well, first off, I do suggest reading through this again or watching these steps and seeing how we could start with the observed. We could find every single expected. We could take every single expected and observed, look at their difference, standardize, and get every single cell chi-squared, add them up for the chi-squared test statistic. So all of this is possible, just very cumbersome. Here are the steps to do it in Jump. Here we go. 1, click the little box right here. Copy to clipboard. Once you've copied to clipboard, I agree with Jackson, hit Control-C or Command-C. So now that we've hit Control-C or Command-C, go into Jump. You can be anywhere inside of Jump and go to File, New, Data Table. File, New, Data Table. Under File, New, Data Table, you're then going to go to Edit, Paste with column names. Make sure you do paste with column names for this. Now that you have paste with column names, the column names will appear at the top. You can change this to age group. This is not required. I did that by double clicking it. It'll make things look nicer a moment later. But you can double click this, change it to age group, not required. Different questions, you might have to change to different things. Now that you have data pasted here, make sure it's red, blue, blue. That is required. Restart and watch the steps if it's not red, blue, blue. If it's red, blue, 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 go to tables, and then go to stack. Under tables stack, we're going to stack the quantitative blue columns. So now double click the blue columns right here till you see both blue columns only right there. With both blue columns in right there, go ahead and click OK. Now you'll notice we have age group, label, and data. This is the frequency of observations right here. This is the combinations of under or the age group with the different labels that occur. So you could change this to like outcome if you want to make it look just like it. Not required. And good to see you here. So now your data should look like red, red, blue. And if you have that, you're good to go. The labels are not so important.
It doesn't matter.
It just makes it look nice. Analyze fit y by x. Analyze fit y by x looks at the bivariate relationship of two variables. Let's go ahead and do it. You need to ask the question, does age group explain why there is a certain outcome? Think about how you're asking it. You can switch them, but I'm going to do it this way right here. Does age group explain why there is a certain outcome? Just do a full circle like going around the clock right there. Do make sure to put data in the frequency. If you don't do that, it won't look right. I'm going to pause on this screen right here. Make sure you get your screen to look just like mine. Make sure the colors of the variables are the same. If they're not the same colors, that'll cause an issue too. Make sure the data's there. Common mistake. That is a big error a lot of people have, Sloan, right there, where the data is not in the frequency and then it isn't in there, it doesn't work. Let's go ahead and click OK right here. And here we go. The people with the most early preterm pregnancies were the 40 or over group. You can see it's a little bit higher right here. You can actually hover over it and see of the age group 40, 36% had an early pregnancy. And you can see the other just hovering over it right there. You can also find those numbers in the table, but we're going to go right down there to the output and the 2.986, that value right there. The Pearson, it's this one over, I'll go to where I can point at it. Right there. That 2.986, we say the Pearson has your p-value. So this is your p-value, and that is your chi-squared test statistic. Jump, chi-squared instructions, copy, clipboard, paste. Yeah, Jackson. Holy mackerel, Jackson. How much easier does it make it, Jackson? 5,000 points. And everyone, amazing. I love when people put, I've pinned Jackson's comments right there. Follow along with my instructions or Jackson's comment right there. Using Jump makes things way easier. That's really how we do data analytics, is we use software, and then we know what the software is telling us. Got an R squared right there. Very little of the variation, because it's not statistically significant. P-value above 0.05. If you understand the concepts, we really go for that in statistics. We'll show how to get the p-value. And thank you, Sloan, right there. Sloan, shout out to Sloan, too. Put in the, I think it was like, what was it, this? It was something like that. That was close enough. Jump is much, much easier. Exactly. And so think about if you're in a class where you have to analyze data or do some sort of statistical test or make a graphic, and someone's like, I know how to use jump and I'm really good at it. You'll be like, hey, yeah. Imagine if you're that person, you're like, hey, I know how to use jump. People be like, oh, let's have you do it. So if you're looking for the p-value, we now have the chi-squared applet directly linked with its own link right here. Thank you. Both Jeremy's right there. Well, no, Jackson, I saw. Yeah, jump is super helpful. I like R. Everyone knows that about me. So check this out. You ready? Oh, we didn't ask this question. Remember how we said it's a 2x4? What are the degrees of freedom for that table? Since it's a 2x4, the degrees of freedom are what? Which tell you the shape of the T. It's a 2x4, so we need to know the shape of the T, which is found by the degrees of freedom. Jackson got it as 3. Notice also that as the chi-squared gets more degrees of freedom, it becomes more normal. And Jackson, I'm going to tell you something really cool right here. You ready for this? I can calculate a p-value. I'm going to do it. Okay, here we go. I think I can do it. Is it this one? I think that's it. Okay, I think I know the formula still. The area above, I'm going to tell you the area above a chi-squared of 70 on degrees of freedom 50. The area is going to be basically about that. So I think if I go to degrees of freedom 50 and go to the area above chi-squared of 70, it's close-ish, right? Close. It's a little higher than I thought. But do you want to know how I knew that? It's because the chi-squared starts to look like what? The chi-squared starts to look like what? It starts to look like the normal. And there's a normal approximation for the chi-squared. So if you want to get a z-score, basically, it starts to look like the normal. And look right here, the center of the chi-squared for the normal approximation is actually where the what's are. This is a little more advanced, but the center of the chi-squared's normal approximation, the mean of the distribution, is where the what's are. What do you think the v right there is, which determines the shape? The center of the chi-squared for the normal approximation is where the what is. The center of it right here, and you can see it also in our applet. The center of the chi-squared normal approximation is where the what is. See it moving? See the center of it moving? The degrees of freedom. Now, the standard deviation is going to be, you take, let's go right here. To get the standard deviation, you can first find variance. Variance is standard deviation squared. You can see right there, sigma squared, standard deviation squared. So the variance is what? Look at the variance right there and look at the variance right here. Or look at the degrees of freedom. This is way more advanced than we need to go. Hey, Rachel, good to see you here. The variance is what the degrees of freedom. Do you see the pattern? The variance is what the degrees of freedom. Do you see the pattern? It'll hold true if I do something like 80. It's double. So if I want to turn variance into standard deviation, I would just take what? If I want to turn variance into standard deviation, what would I do with it? We went really advanced to end this question. I just find statistics so cool. It's sad. If I wanted to turn this into standard deviation, and I picked 50 for a reason, I'd do that. And so then why did I pick 70? Pulse secure, go away. Sure, extend it. So does anyone know why I picked 70? And then I said the area above 70 is about, oh my gosh, go away, pulse secure. I like my secure net connection, but not right now. Does anyone know why I estimated it to be about 2.5%? Because the normal approximation is, so why would I do that? Good job, Matt, right there. Because using the normal approximation, it's basically 2 standard deviations above the mean. And 2 standard deviations above the mean is about 2.5%. So, but here's the problem with everything I just said. So thank you for everyone listening to this huge rant about the normal curve and the chi-squared curve. The normal approximation doesn't work when what? Ooh, that's interesting. The normal approximation doesn't work when the degrees of freedom are very what? Hint, doesn't work, doesn't work, doesn't work, doesn't work, starting to work, probably works pretty well. Yeah, Jackson, that's exactly that. Jackson said it. Yeah, that's exactly it. The normal approximation of the chi-squared only probably works pretty well after about degrees of freedom 50. It's not like it works at 50 and doesn't work at 49. It's just that the normal approximation of the chi-squared works better at higher degrees of freedom because the chi-squared approaches the normal. The chi-squared's a right-skewed distribution, and the right skew starts to diminish or go away as the degrees of freedom increase. So at some point you reach where there's only going to be small differences. And then if you wanted to do the calculations by hand, like let's say you didn't have an applet, you could use the normal approximation to get a pretty good estimate of what the p-value is using a chi-squared normal approximation. Does that make sense, Jack? That's why the normal is so powerful, because using normal techniques, you could figure out answers to chi-squared questions after about 50 degrees of freedom and have a pretty good estimate. Just to repeat, I was able to estimate the p-value to be about 2.5%. I said degrees of freedom 50, and I said we have a chi-squared right here where we have a chi-squared of 70, and I said it'd be about 2.5. You carry the extra decimal, you see I'm a little bit worse. 2.5 does round to 3%, but it's 3.2%. So I was off by 0.07 using a normal approximation. So degrees of freedom acts as the mean with the center. And then the shape gets more normal as it increases. So right here, you can see on this applet, this is a really great applet created by Matt Bogner at University of Iowa. He gives you the center right there, which is the mu, the mean, or the expected value that says expected value of x. Then we have the standard deviation of x right there, and the variance. I forgot they give you standard deviation. I know, it's super interesting. It's like the normal curve is so powerful. Central limit theorem brings things to the normal curve. Chi-squared distribution. Yeah, I should find out more. Like, did Gauss make... I don't know. Wait, Gauss made the normal. I'm trying to think who made the chi-squared. What's his name, full name? Can't think of Gauss's full name right now, but he made the normal. Anyway, is the end of this question right here. We'll finish it. The p-value is way greater than any alpha level that we would ever consider. Since the p-value is high, we let the null fly. So p-value is high. There is not evidence for the alternative. Make sure to know to write your full sentence right here. My p-value is high. I do not reject the null. I do not have evidence for alternative. Carl Pearson. Oh, he did. Sloan, I should have known that. Yeah, well, there you go. And that's what Pearson's named after, my Pearson. Pearson was a mathematician. He was like 1910 or so. Like, it's so weird. Statistics is a really rather modern field of study. The whole idea of using mathematics and figuring out probabilities based on this kind of stuff. Probability's been around a long time, but statistics has not. I think it was the first. There was like 1670 or something is when statistics first is said to have been thought of. Pearson on jump 2. Oh yeah, well yeah, big test right there. And Carl Pearson. So here, yeah, he was almost around when my parents were born, like 1936. Pretty interesting. And there's a big one we name Akeike. I'm not going to show the... Here we go. This is one of my favorite mathematicians. He was alive when Pearson was alive. So this gentleman right here, you think about the overlap that Hirosagu Akeike... Sorry, I mispronounced his first name. I'm pretty sure I know how to pronounce his last name. Akeike. But yeah, Akeike came up with Akeike's information criteria, which... You'll get this right here, and this hasn't been updated. As of 2016, has 17,000 citations. A lot of times people are citing it now, and they don't even cite it because it's just commonly used. He got Japan's highest award. Google Doodle did a thing for his 90th birthday. He's also the mentor of Humphreys Bosdogan from our University of Tennessee. So, yeah, Akeike, really great statistician right there. It probably did, Jackson. Yeah, there's... I'm trying to think. The guy who started it, it's like 1660, but Akeike, yeah, think about all those citations. There's like a site that looks at it too that shows how often it's been cited. But Akeike's information criteria is a very, very important idea in statistics. And I might have the notes still open on it. Let's log in. Oh, wait, maybe it's got my old stuff on it. Where's the thing Pearson's on? No, it's just login crap. Okay. But Akeike's information criteria is actually very easy to use. We're kind of going on a rant here again. Check this out. We'll just do weight of a car explained by the miles per gallon of a car. So let's have miles per gallon explained by weight. That makes more sense, right? So if you like cars, you might want to know what's your miles per gallon. and maybe the weight of your car explains it. So we can easily visualize this model right here. I don't have my libraries open to visualize models. So we can visualize this model. It's going to be mad because it's too large. And you can see right here that cars that are generally cars that weigh more generally get worse miles per gallon. But do you notice here that this model might have a bit of an issue with what? And I'll give you a hint. Ooh, it's going to be kind of cool. This model might have an issue with what? What do you think the issue is for 1,000 points? I'm kind of seeing some like this right here. What do you notice in here? If you notice, the points are kind of above. You can say goodness of fit. If you did a goodness of fit test, it would be if it is the line a good fit. So I can actually check that. The goodness of fit would see is the line a good fit, and the answer for that is no. We do not pass the goodness of fit test for the linearity, and I can check the equal spread. The equal spread is actually very good. So, what's really cool is we can do these things rather quickly at the higher level. Equal spread is plot thickening. High p-value indicates good because the null hypothesis is that equal spread is good. Normality of residuals, we want them to follow the normal curve, which is actually a goodness of fit for the normal, and it actually does fine because we don't reject that. Or these all right here we assume are good. But here's how we can do linearity. Watch this. Let's go to a function called choose order. This is going to choose the polynomial what for our model. This is going to choose the correct polynomial what for our model. So this is helping us choose the correct polynomial what. It's called choose order, and the order is the degree to which you raise something to. So the higher the order, the more points of inflection. Like the second degree polynomial would just be the, let's go here and do max order. Exactly. And you see how that's just the line? And then there's the, you know what's really interesting about this? Do you really see any differences between the red and the green? If you look at red and green right there, do they look really different at all? The red and the green. And this is what's so cool with what Ake did. And you'll see it here when we look at the values of these. They don't look any different, right? These two things look exactly the same to me. So the way Ake's criteria works, there it is, Ake's information criteria corrected. That is the second degree polynomial order with the red line, and the third degree polynomial order is pretty much overlapping it. Yeah, so it's exactly. We can write out these equations and all that stuff right here. This is what we do at higher level statistics. We make these models, and I want you to think about this. So don't even worry about it, because you remember you think that the third is not really doing much for us. So if you look at Ake's information criteria and you look at R squared, what do you think is better, higher or lower Ake information criterias? That is Ake's information criteria corrected. He did a little extra later on. He corrected it, put some corrections in there. Lower is better. And we go over the mathematics in BAS 320 and talk about how it's based on standard errors, or excuse me, sums of squared errors. So you can see the calculations he did, but you have to know how to use it. And the second degree polynomial is the best, because here's what we can do, which is pretty fun. We can go crazy and go to a 10th degree polynomial. And then if you look at the output right here, you can see that the best one is this. So actually what he's showing you is by fitting these crazy higher order polynomials, you're probably making worse models. Like this is a horrifically worse model than up here where you just fit the line, even though it's bending through the data a whole ton. So Ake's information criteria can be used to compare models to let us know which model is closer to the truth. And this is pointing to using a second degree polynomial to kind of fit through the model and explain it, that there's kind of this bend. And I just think it's so cool that he came up with this idea to do model comparison, and it looks like that is going to be the best model, that second degree polynomial. So that's kind of a little bit more of the advanced stuff we do, especially in 320. And that's, you have to know what you're looking at. And that's what I'm totally mispronouncing his first name, Hirotogo. Wait, how are there alternative spellings of his name right there? Does order need to be independent? It kind of is. In what way, Jackson? In what way are you thinking order needs to be independent? So the order is just like the mathematics you're doing to the, here, I'll go ahead and make the model right here. So we go over here and we go poly weight to the second order, and then we make a summary of our model, and there it is right there. There's the coefficient So you could end up writing this out right here. Like if we wrote this model, the mathematics for this model would be, it's very similar to how you do regression, just general regression. I think so. I would need to have to be careful I answer that because I'm not exactly sure. We want to predict miles per gallon, right? Miles per gallon predicted is equal to intercept. So there's your intercept value. So intercept plus weight. Well, let's put the coefficient before it. Negative 29.115 weight, and then plus 8.64 weight to the second degree. And so if you look right here, that's the linear term, and then this is the quadratic term right there. And so you basically have your form of like y equals kind of, what is it, mx plus b. So this would be b plus mx, and then this is plus, what is it, like, I don't know, m1x. I don't do this kind of notation. Or so, well, kind of doing it right. We call it b0 plus b1x1 plus b2x squared. Does that make sense right there, Jackson? We kind of went more in depth, but you can see the coefficients right there of the first degree polynomial, which is this is the polynomial to the first order, hence why we didn't raise it. This is the polynomial to the second order right there. So I said do a polynomial to max order 2 on it, and it gave me the coefficient of the linear term, the coefficient of the polynomial term. And then we could write the model. But what's even better is we don't need to write the model. We can just say predict for those cars, and there's the predictions. So that's all the predictions for those cars right there, the predicted miles per gallon, which comes from the polynomial model. So rather than solving it, we can do that. We can ask for the residuals. We can just say residuals of the model. There's all the residuals. Then we just have to know what residuals mean. So I think it's super cool. Like, it's neat how fast we can get things. And then you have to understand what the concept means of a residual. You have to understand like how the model's making predictions. That it's just going to solve a mathematical equation for you and get you an output of a predicted value. Actual minus predicted would get you the residual. And then you could take, I'm having some fun right here. Well, we know what the actual is. So the actual is where these dots are. So like the dot is the actual. So can I turn that into a ggplot? Let me go over here. Library ggpub_r and ggscatter. Okay, 2 seconds. I'm gonna see if I can turn this into a really cool plot right here. Wait, here we go. Call labels. Where's labels? Panel labels, short panel labels, label. Okay, here we go. We're gonna try something pretty fun right here. I was like practicing. Ooh, exactly. They're using the same test data set. Okay, the Y, really? Exactly, same thing we're doing right here. Okay, so they are object exclosure. What is an, oh, empty cars. There we go. This is a local regression. That's what that stands for, local regression. It's basically does a window where it tries to smooth a regression line across. Let's add here label equals row names of empty cars. Is that going to work? Ooh. Now let's go here, store this into plot, and then go to plotly. That's what I want. And go to ggplotly and do this. Kind of. Well, it's a little messy with so much on the screen. That's what you get when you have a whole bunch of points. But we could zoom in on it. So you see right here, the Mercedes 24D. The Mercedes 24D has these values. I want to also show the residuals. I could probably have to calculate those and throw them into this model. But these are kind of the neat things we can do with coding. It's also, yeah, I agree, Jesse. I love it. This is the kind of stuff I love, and we teach in 320. So I've been working on this. And look, these are confidence bounds for the predictions. I think these are prediction intervals. So you would expect 95% of observations. Look, there's only a few, 1, 2, 3, 4, 5-ish that are outside of here. So you'd expect 95% of the observations. Ooh, a little bit outside, but you'd expect 95% of the observations. We're not doing too well. Maybe it's an only 80% prediction interval. So confident true right there is the confidence intervals. We could look to see if confident has anything else to see if there's some way to set the confidence level. Confident level. There it is. Yeah, it's 95% confident. So we could increase it to 99% confident. And look at this. What happened since I increased this to 99% confident? Since I increased this, is it going to show up? Since I increased it to 99% confident, what happened right here? And you can see the same concepts that we've been talking about. If you go from 95 to 99, there it is. Yep, look at that. So same sort of concepts, 95% confident, 99% confident. Go down here to 50% confident. So now here's 50% confident, and there you go. So 50% confident, 95% confident, and same things apply about how the intervals work. And that's why I love working with data, because the more you understand it, you understand what's going on with the confidence intervals right there, how this is only a 50% confidence interval. You notice a lot of the points are outside, like the vast majority, probably more than 50% it looks like. So would a third order be cubic? That is correct. So we could fit the cubic model. Sometimes these are a little harder. Let me go, I'm going to do this right here. I think I have a meeting in 5 minutes. Fitting a cubic model in R and plotting it. All right. How to plot polynomial regression, and it's recent. We like recent articles. Okay, they're fitting their model. They're doing the term. Oh, they're just doing it that way? Okay, so they've got some random data they created. They got a Y. They're predicting, okay, there is a, okay, and they're adding the lines to it. That's pretty nice. Or they're adding the equation. It's not bad code. Fit the linear model with, oh, interesting. I've never done it this way. Okay, let me try it. I did not know this. And then we're going to take... Okay, so there's that. Okay. Let's go ahead and grab their code. And we're going to do the same sort of thing with our time right here. So we are going to take their code. And the first thing they did is they fit their model. So the fit of their model is going to be, and we need a data equals. We use data equals right here, empty cars. And we are predicting the weight of a car from the miles per gallon. And I've never used this sort of notation for it. I've never done the I, raising it to. So let's hope this works. And it works. So that's new to me. There's the predicted. There is the, they're sorting it and they're storing it of their X variables. This is the name of the X variable. So this has to be MPG. So we have to change this X to MPG right there. And it's just that X, I believe. We don't have the XI data frame. What is, or the XI object? Where's that? Because that's $XI. Let me see what that returns. Dang it. I'm going to get stuck on this real quick. Return index. Okay, what does this create? Oh, no. They must have done something earlier that I didn't see. Where's the XI? What is this code? What is, I gotta run the exact code. I want to do this. I got 2-3 minutes. Is the formula, since it would be. Great job right there. Wait, where's the next code? Okay, here we go. I love looking at code. It's fun to me to see what people do. Then why did this run? Oh, I know what it is. Okay, I know what it is. I know what I got wrong here. This is empty cars, $, miles per gallon. Gosh, can't believe I did that. There we go. Okay, good. Whoa, look at that graphic over there. Okay, so now we need to clear the plot. Okay. So, I think we're good. Plot new. Yeah, wait, where's the plot? So they already have their plot on here? Okay, where is it? Seconds to go. Oh, well, that's not the right line. Okay. Well, we got close. Yeah, so we got close. We didn't quite get it. We'll have to try again. I got to go off to the meeting, but does that make sense, Jackson, right there? I got close to doing it with the methodology they're doing it, which I've never done before, using that methodology to get the plots. But there's the model right there with the terms to the powers, like you're writing out right there, where it's. Does that make sense? Like we usually put the intercept first. The third order, well, according to Akaiki's information criteria, so this is what we can do really quickly right here. We can go to choose order, and I think I still have my model as M. According to Akaike, the second order is the best. So according to Akaike, the second order would be the best because it has the lowest Akaike information criteria. So that's how you would look at it right there. You'd be like, second order is the best. And think about it, because the third order, I'm going to go here after this. The third order, just visually speaking, looks a lot like the second order. And so basically, it really doesn't help us, which is also seen in the R squared adjusted, which has decreased. R squared adjusted is R squared adjusted with a penalty term. So generally, you look for the highest R squared adjusted and the lowest Akaike's information criteria, because it's still kind of like R squared. Yeah, well, I'm glad people got... This is what we do, and if you are in any sort of science or economics or sports industry, this is how you can pick between models and know that your model is getting closer to the truth. So a little bit of advanced analytics to end. Until then, bye for now, everyone. Bye!